Hello everybody and welcome to this video lecture on operations research code ORMS 1020, and we are now starting chapter 8 about duality. So this is a chapter 8 from the lecture notes linear programming with SPICE, and this is a slightly different chapter than what we had previously. So previously we considered these things that we are learning through examples. So now in this chapter we consider LPs, that's the linear programs or linear optimization problems, rather formally or theoretically if you like, and if you don't, I'm sorry about that. And what's going on here? So we start with first section called standard form, dual standard form, and slack form. So this is a rather lengthy section, and what's the point there? We study how to represent a linear program LP in a very different but equivalent form. By equivalent form we mean that it's actually the same problem, but we represent it slightly differently. And then the actual duality. So duality is the topic of this chapter. That's a thing between two different LPs, and this is given in the second section called duality theorems. Alright, so let us start section standard form, dual standard form, and slack form. And we start with the standard form, or what I call a standard form. So word of warning, there is no standard. What is a standard? So for example, GLPK thinks a standard form something completely different than this, and some people consider standard form to be a minimization and not maximization. I like maximization for some reason, so I take max to be the standard. So the standard form LP here, equation 8.1, it is of this form. So it's a maximization. You maximize something, here it's called Z equals C transpose times X. Then it's subject to some constraints, and in the standard form we assume that we have upper bounds. So this is the key thing here. This is what makes the form standard form. So if there are lower bound constraints or equality, or not all the constraints are same, then I do not consider it to be a standard form. So in standard form all the bounds are upper bounds. And also important, I assume in standard form the sign constraints here. So all the decision variables x, x1, x2, and so on, they have to be non-negative or positive. So again, something you might think that non-negative and positive are different thing, but I assume that they're the same thing. So for me 0 is a positive number. Alright, also you might notice that we have actually used and even maybe implicitly assumed that all our LPs are in this standard form previously. And okay, so if you look carefully the previous chapter, so it may seem that we have restricted our considerations only to the standard form LPs, especially in the previous chapter where we considered sensitivity. And okay, now it seems that we may have a problem here in the sense that our analysis is not valid for all LPs, only LPs of this standard form. But we are actually fortunate, this is not the case. Indeed, any LP, any linear program can be written or rewritten in a standard form. So if we are given an LP that's not of this form, we can, if we wish, transform it into into a standard form, so the form like this. Okay, so yes, in general LPs can take many different forms, and yeah, to be completely honest here, we actually have not even given a formal definition of an LP here. And well, actually we continue to do so. I guess that the formal definition wouldn't help much. I think it's more, let's be more intuitive. I hope that everybody by now understands what's an LP, and there is no need to give a formal and complicated definition. So indeed, as usually in these notes, we proceed with problems and examples. and to start this, let us start with what I call a simple example. So this is a relatively simple LP that is now not in the standard form. So this is example 8.2, which I call simple standard LP transformation. So what do we have here? So let us not have any nice story how this LP, where this comes from. It just comes from somewhere. We are given an LP. So we consider the following non-standard form LP, which I call 8.3. So it's a minimization of something like this, and it's subject to two constraints. First, we have something like this with a lower bound 3 and something like what we have here with an upper bound 42. And I have this sign constraint, so there are 3 decision variables and all of them have to be non-negative, or as I call them, positive. And then I have these Roman numerals here, 1, 2, 3 and 4, just for reference purposes, so I can refer to these lines. Since now I'm going to change these lines in order to make this LP a standard form. Alright, so that's our job now, to write this LP 8.3 into a standard form. And as it's typical, let's start from the top and go towards the bottom. First, objective. That's the line 1 here. And this is a minimization. Okay. And in standard form, we want to have a maximization. So how do I cope with this? Can I change a minimization to maximization? So first, if you think about it, it may look a bit difficult, since, I mean, if you want to minimize something, then it's kind of very different thing if you want to maximize something, obviously. But from the mathematical point of view, there is really not much difference, and this is, I mean, multiplied by -1. I mean, if you want to maximize z, some function, it's the same as, minimize, we are minimizing. So if I want to minimize z, it's the same as maximize -z. I think this is clear, yes? So z is like this, so minus z is, you multiply everything by -1, and then this minimization of z, 8x1 minus 10x2 plus 7x3, that's the objective, which I call 1, is the same as, and here I have a typo, this will be corrected in the notes soon, but I will continue this video lesson anyway, so don't be confused that this mean will be then in the notes, of course, max. So obviously this is a mistake. So minimization of z is the maximization of -z, and then it's equals, okay, 8x1 is minus 8x1, minus 10x2 is plus 10x2, and plus 7x3 is minus 7x3. And I keep here the minus sign. I could have denoted, for example, w is minus z, or just maybe abuse the notation and use this new z for the minus z. I could have done that, but then in solving this obviously solving this first LP, if I solve then the standard form that will come out of here, then the solution, I have to switch the signs. Okay, formally this is maybe a slight problem. In practice, I don't think it's a problem at all. It's quite often you have maybe a the opposite sign that was supposed to be, but from the practical problem I think it should be clear if you have to say change the sign then in the interpretation or not. Alright, so that was the first line. So from the minimization, again sorry about this, this would be max, we turn into maximization. What then? Then line 2, we have to look about that. It's a lower bound. It should be an upper bound. So what do we do with that? Well, I mean, obviously we do the same thing at from min to max. We multiply by -1. So here you can see, you have learned this in school I hope, that if you have an inequality something is greater than equal to something else, if you multiply it by a negative number you have to change the inequality the other way around. We could actually multiply this with any negative number, not 0, and that would still do the trick, no problem there, but multiplication by -1 is obviously the easiest thing to do. We just change the signs, so we do that. So 9x1 plus 5x2 minus 3x3 bigger than or equal to 3 is the same thing as, let's see if I did this correctly, so plus 9x1, I have minus 9x1, then plus 5x2 goes to minus 5x2, and minus 3x3 goes to plus 3x3 less than or equal to minus 3. Okay, so that's the same inequality. So the inequality or the constraint 2 here, it is the same as 2, and I put here prime just meaning that it's the same as 2 but written in a different form. So that's now in the constraint now is an upper bound as we want to have with standard form LP. Okay, let's look at then the following lines. So then there is a constraint 3, x1 plus 6x3. So x2 is not present there, or it has a 0 coefficient, the same thing. And this should be less than or equal to 42, but this is an upper bound as it should be. So I don't have to do anything with 3. And then x1, x2, x3, they are all non-negative, so they are sign constraint, so they should be positive. And this is indeed what we should have in the standard form LP also, so nothing to be done here, right? So we are actually finished. So we just collect all that we have found out, and now this maximization here is the correct one. So this mistake here was corrected here. So we have an LP maximize minus z, something like this. Constraints are like this. And now if you look at this 8.4, what does it look like? It is of the form 8.1. So we have found a standard form. And in the end of this small lecture, let me emphasize a little bit what happened here. What happened here is that we wrote this problem LP 8.3 in a different form, 8.4. But what do I mean by this different form? It looks different. Yes, it's written in a different way, but it is exactly the same problem. And it is even exactly the same problem in detail, if you want, that all these lines here are basically the same. So I can replace 3.2 with 2 prime, and it's the same. Nothing is different really. So the solution of 8.5 is exactly the solution of 8.3. So this, we have rewritten the LP in a different form. We have not changed the LP as such. Of course, how to solve it may be different, but LP is not different. Okay, that was the first part on chapter 8, and we continue in next videos. See you.